Hello and welcome to Math 152. As you have known, classes are cancelled due to the deep freeze. But luckily, internet is never down. That's why we are meeting here to continue our discussion on section 6.8, which is indeterminate form and L'Hopital rule. And we will start a new sections. In the second video, we will talk about section 7.1, which is on the new topics, which is techniques of integrations. And we'll do that later. Now, so back to what we were discussing on Monday, we were talking about something that we know we call indeterminate form of a type 0 over 0. Now, remember, 0 over 0 is never a thing in math. So we don't really talk about 0 over 0. When we say indeterminate form of the type 0 over 0, we are talking about limits of this type where the fx will go to 0 when your x approaches a, and your g of x will go to 0 when your x approaches a. So when you are studying the limits like this with this two property, then we say that this limit is indeterminate, has an indeterminate form of the type 0 over 0. All right, so let's look at an example. This is something that you can actually do in Calc 1, which is evaluating these limits. Now in Calc 1, the way you evaluate these limits is to first investigate what happened when you kind of like substitute x equal to 1. So if you put x equal to 1 inside these expressions, you will see that here you have a 0, here you have a 0. So you know that this is no good because you have 0 over 0. So indeterminate form of the type 0 over 0 is something that you actually already encounter in Math 151. And if you remember, the way we deal with it in 151 is to do some algebra. So for example, in this case, we factor out the x, and we also factor out x squared minus 1. And then, well, there's cancellations that you can perform because when x approaches 1, x is never equal to 1. Therefore, x minus 1 and x minus 1 is never 0. So you can divide both of this and reduces the expressions to this. Which is right here, and we haven't evaluated the limit yet, so you still have the limit, you still have the limit, you still have the limit. Make sure you write all of that. And right now, it is safe to evaluate this limit because when x approaches 1, this is 2, this is 1, that's no problem. So your final answer is 1 over 2. Now, L'Hopital rule says that you don't really have to do it this way. There's another alternative. The alternative is that if you have indeterminate form of the type 0 over 0, what you can do is take the derivative of this, which is 2x, and the derivative of x is 1. So the derivative of x squared minus x gives you 2x minus 1. And then you take the derivative of this guy also, which gives you 2x. And then L'Hopital rule says that after you take the derivative, you try to figure out whether or not you can evaluate this limit. And evaluate this limit is not a problem. When x goes to 1, this goes to 2, this goes to 1. So L'Hopital rule says that this limits right here will be the limits of the original questions that you try to answer. And that's it. That's what L'Hopital rule said. And make sure that as a habit, every time you apply a L'Hopital rule, you might want to write H right here to indicate that the reason why you have this limit is equal to this limit is because you apply a L'Hopital rule. So you get the same answer from before. And one key things that I talked about on Monday, I want to remind you again. So this is what L'Hopital rule say that it says that if it's in the indeterminate form, so you take the derivative, instead of evaluating these limits, you evaluate these limits. And if this limit exists, well, then this limits, the original one will be this limit. But it has to be in the determinate form of the type 0 over 0, infinity over 0, infinity over infinity, and that kind of stuff. Like, for example, if it is not, you cannot apply L'Hopital rule. For example, if I ask to evaluate limits of x squared over x when x goes to 1, this is easy because you can directly substitute all this thing with 1 and you get the limit 1. But as you can see, if you didn't know that, I mean, if you didn't check whether or not this is indeterminate form, obviously this is not indeterminate form, but if you apply L'Hopital rule and you would say that x squared derivative is 2x, the derivative of x is 1, so L'Hopital rule says 2. L'Hopital rule didn't say anything like that, okay? If you look at the theorem in the book, L'Hopital rule only says that when you have indeterminate form, then only you have this limit, this relationship, provided that this limit exists. So you cannot claim that by L'Hopital rule the answer is 2. Which means that every time you try to apply L'Hopital rule, you really have to check whether or not they are one of this indeterminate form. So we have the indeterminate form 0 over 0. We also have the indeterminate form infinity over infinity. It's the same rationale. The reason why is infinity over infinity is because when you try to evaluate this limit, the limits of the top parts goes to infinity when x approaches a, and the limits of the gx also goes to infinity when x approaches a. That's the reason why we say this is infinity over infinity. So it's just an expression. Indeterminate means that, well, this limits, when you run into this kind of trouble, the limit might not exist. The limits, if it exists, it could be equals to one particular number, or it could equal to another number. It's just really no way for you to determine it beforehand. Therefore, you have this terminology indeterminate. So let's look at an example. This is also something you know how to do in Calc 1. If you ask to evaluate limit x goes to infinity, by the way, the a here could be anything, could be a number, could be infinity. L'Hopital rule still works. So this is a question that you know how to do in Calc 1. If you ask to evaluate this limit when x goes to infinity, one thing that you can do is to like multiply 1 over x squared here, multiply 1 over x squared here. That's the reason why you have this. I can do this because this whole thing just turns out to be 1. So I'm not changing anything. So this expression here is exactly the same as this. I can do that also because my x is never 0. It's something that's a very big number, so I can do all that. And the reason why we change it to this form is because we know that when x goes to infinity, this guy go to 0, this guy go to 0. That's the reason why you know that it is 1 over 3. Okay, so make sure you write this limits because you haven't evaluated any limits. This is still this guy. And then when you evaluate the limits, then only you drop the limit sign and write 1 over 3. So this is something that you know how to do in Calc 1, but the L'Hopital rule says that you don't really have to do any algebra. You take x squared minus 1, differentiate it. Just get 2x, 3x squared plus 1, differentiate it, and get 6x. X is never 0, so you can cancel these two out, which gives you 1 over 3. So you're kind of evaluating this constant limits. Obviously, you get 1 over 3. And one thing that I keep mentioning and you must remember is that we are not taking the quotient rule of this guy. We are just looking at this, take the derivative, looking at this, take the derivative. All right, now L'Hopital rule is really something that we need when you run into this kind of problem because there's really no way you can simplify it. This is log x, you cannot really factor anything out of log x. So can we use L'Hopital rule? I don't know. We have to check whether or not it's in determinate form first, okay? So log x is a graph that looks like this. When x goes to infinity, obviously log x will go to infinity as well. So this is going to infinity. This is also going to infinity. So we do have infinity over infinity. So this is really an indeterminate form of the type infinity over infinity that's perfectly set up for us to use the L'Hopital rule. And we're using it right here. That's the reason why we have the h right here. So you look at log x, you differentiate it, you have 1 over x. You look at x to the power 1 over 3, you differentiate it, and you have this. Now, and you can still apply L'Hopital rule here because when you take x goes to infinity, this guy go to 0, this guy go to 0. So now you have 0 over 0 type of indeterminate form. So by right, you can still use L'Hopital rule, but you might not want to do that because by doing that, you will have, things are getting more complicated and you will still running into a 0 over 0 and you will have to keep differentiating and that's just no end. Now, another way to get out of this mess is to just simplify this. Now, the algebra tells you that something over 1 over 3 will give you 3. That's the reason why you have here 3 here. And then this is negative x to the power negative 1, x to the power negative 2 over 3. So when the base is the same, you have division, so this power have to subtract each other. So it's negative 1 minus 2 over 3, which gives you 1 over 3, negative 1 over 3. And negative 1 over 3 means that you have this, so you can rewrite this thing as this. You can also take out the 3, right? As limits, you can take this thing out. And once you look at this, you will know when x is unbounded, going to be unboundedly big, you know the limit is 0. As simple as that. So L'Hopital rule says that the final limit will be the same as this if this limit exists. It exists, it's 0. So that's where you apply L'Hopital rule. So that's the things you need to know. Make sure that you check whether or not you are in one type of indeterminate form or the other before you can actually use L'Hopital rule. Otherwise, you will run into trouble. Now, another type of indeterminate form will be the type of 0 times infinity, also known as indeterminate product. So when you have 0 times infinity, you also don't really know what the answer is. It could be 0, it could be undefined, it could be something else. You have no idea. Hence the terminology indeterminate. Okay, and by now you should be able to guess why we say this is of the form 0 times infinity, because when you evaluate these limits, turns out that the f will go to 0 when x approaches a, and the g will approaches infinity when x approaches a. When this happens and you are asked to find this limit, we say that this limit is of indeterminate form of this type. Okay, example. The easiest one probably this. So when x goes to infinity, obviously everyone knows this will go to infinity. And when x goes to infinity, your EX graph will look like this. Okay, E negative x is actually 1 over this guy. So when things are small, this is big. When things are big, this is small. So you can obviously see that when x goes to infinity, E negative x approaches 0. So this is approaching 0. So you do have that type of 0 times infinity. So the way you deal with it is to try to change it to something that is like this, which we already know how to solve it, or something that is like this. In this case, this is pretty easy to do because this is x, but this guy is just this. So this is exactly this. So and by the way, we haven't applied L'Hopital rule yet. We just changed the form. And now check what happened when x goes to infinity. So this will go to infinity, this will go to infinity right here. So now you are in infinity over infinity form, and you can apply L'Hopital rule by differentiate x, which gives you 1, differentiate ex, give you ex. So this limit is the same as this. So when x goes to infinity, you know the thing goes to 0. That's the reason why it's 0. So L'Hopital rule says that that limit is 0. Okay, that's an easy example. Well, let's look at this problem. So when x goes to 0, this x goes to 0, obviously. X goes to 0 from the right-hand side, though. So that's the indication that this thing is one-sided limit. So for log, what happens to log when x approaches 0 from the right? So log x have a graph that looks like this. This is 1. So when x approaches 0 from the right-hand side, you know that log goes to negative infinity. By the way, when we say infinity, it doesn't really matter is it a plus infinity or negative infinity. Your L'Hopital rule still works. Okay, so now you see that this thing here goes to 0, this thing here goes to negative infinity. So it is an indeterminate form of this type, and the way you deal with it is to try to change the form. So, well, we can write x as, so you can write x as 1 over x. That's the reason why I'm writing x as 1 over x. And so they are still the same thing. So this thing here and this thing here, they're the same thing. I haven't evaluated the limit yet, haven't applied L'Hopital rule yet. I'm just changing the form. Now and remember, before you apply L'Hopital rule, you have to check what happens. So try to imagine when x goes to 0 from the right-hand side, this guy now goes to infinity. This guy now also goes to infinity, negative infinity, but it doesn't really matter. So we can apply L'Hopital rule. And as you can see, I didn't follow my instructions, so this should be h. So now I apply L'Hopital rule, differentiate this, you have this, differentiate this, you have this. Do some algebra operation on this, simplify this as much as you can, and you have that, and that limit is obviously 0. So L'Hopital rule says that, yeah, this limit is this, 0, no biggie. You might want to say that, yeah, whatever, so whenever you have limits of this type, always 0. Well, it's not necessarily the case. It's called indeterminate for reasons. It could be something else also. And this example will show you that it can be something else. So x goes to 0 from the right-hand side, so it involves trigonometric functions, so you better know how all your sine, cosine looks like. So that's how sine looks like when x goes to 0. This thing goes to 0, so this whole thing will go to 0. So this is approaching 0. Cotangent is 1 over tangent, so 1 over tangent is 2x. Is 1 over sine 2x over cosine 2x, and this is the same as cosine 2x over sine 2x. And you can see what happened when x approaches 0. This guy approaches 0, so this guy approaches 1. So it's no good, right? You are going to get positive infinity right here. So this is indeterminate form of a type 0 times infinity, okay? Indeterminate product. So how do you deal with it? You change it to either 0 over 0 or infinity over infinity. So the way we will try to do is to fix the sine 6x and write cotangent 2x as 1 over cotangent 2x. Because cotangent is 1 over tangent, so 1 over cotangent is going to be tangent. I haven't used any L'Hopital rule or whatever. I'm just simplifying, rewriting the expression. It turns out to be like this. Now try to see what happens when x goes to 0. This will go to 0. This is going to 0 from the right-hand side. So this will go to 0, and this will go to 0. So now you have indeterminate form of the type 0 over 0. And therefore, again, this qualifies for you to use the L'Hopital rule. So you just have to take the derivative, which is this. Take the derivative, which is this. And then, so, I mean, we can evaluate this limit already. Actually, I just want to rewrite this so that it's easier for you to see that. This term here is here, and then again, secant is 1 over cosine. So you have 1 over cosine. You will have these terms. And when x goes to 0, you see that nothing bad is going to happen. This will goes to 1. This will goes to 1. Cosine graph looks like this, right? So when x goes to 0, this guy goes to 1. This guy goes to 1. So the limit is 3. Okay? So it's indeterminate because, as you can see, we have the 0, we have the 0. But then this is not 0. Okay? So it's indeterminate for this reason and of this type. Exactly because of this 0, infinity, 0, and then like here 0, infinity, and like here 0, infinity. So that's that. There's another type of indeterminate form. Now this indeterminate form is a type of infinity minus infinity. This is also known as indeterminate difference. Yeah, so you don't really know the answer to this like right away. So we will have to do something about it. So indeterminate, simply because, yeah, we don't really know. It's not something as simple as this where you can tell what's the answer. So, so the way we deal with it is same thing. We try to rewrite this, put it in some other algebraic form. So one thing that we can do is to put it as a form that looks like this, which means that we need to have a common denominator. Now, before we do that, let's double check one more time. When x goes to 1 from the right-hand side, this goes to 1, this goes to 0 from the right-hand side. So this is really infinity, the limit. I'm saying, okay, don't get me wrong, I'm saying that this limit is positive infinity. Okay, and what happened to this limit? This limit, log x against log x looks like this. This is why you approach it here from here. So you know that this is actually positive infinity. That's the reason why we have that infinity minus infinity form, because this guy limits is infinity. This guy, the limits is infinity. The limit. Okay, so, well, we can use L'Hopital rule for this. So rewrite this as this, which turns out to be this. It's nothing. I haven't do any limits evaluation yet. I am just simply rewriting this. And now, let's see what happens when x approaches 1. So this approaches 0 because x approaches 1, but log x approaches 0 when x approaches 1. So this approaches 0. This approaches -1. This approaches 1. So the whole thing up here approaches 0. Okay, when the limit is approaching 1 from the right-hand side. So we have 0. How about this guy? Well, when x approaches 1, this approaches 0, this approaches 1, so this thing, the product approaches 0. This approaches 0 because log graph is like this. When it approaches 1, this approaches 0. So the bottom here, the denominator is 0 over 0, 0 minus 0. So it's again 0. So you have 0, 0 indeterminate form, which allowed you to use L'Hopital rule. So you use it, differentiate this whole thing. Well, you have to differentiate this first, which you'll have to do it using product rule. Fix the x, differentiate log x, and then fix the log x, differentiate x, and then differentiate minus x, give you this, differentiate 1, give you 0. So that's that. And differentiate this. This is again product rule, same product rule as before. And then differentiate log x give you minus 1 over x. With this minus. Differentiate minus log x give you this. And that's that. And let's see what happens. Let's rewrite this to simplify. This is obviously 1. This is obviously 1. So I'm basically just rewrite this one more time. So you have this. And before you do anything, double check what happened when your x approaches 1. So x approaches 1. Oh, by the way, this is cancelled out. Right, good, cool. So we can again rewrite this as this, tidy up things a little bit. And right, so let's look at what happened when x approaches 1 from the right-hand side. This approaches 0. This approaches minus 1. This approaches 1. So the whole thing approaches 0. This approaches 0. And you'll be like, oh, no, we still have 0 over 0. Why is that? Life is cruel and all that kind of stuff. Well, yeah, no, it's too bad. You still have 0 over 0. Well, what can you do with it? Well, it's still 0 over 0. L'Hopital rule still applies, so which means that, let's just do one more L'Hopital rule. And just do it because you can actually do it, right? So take the log x, differentiate it. It's 1 over x. Take the 1, differentiate it, 0. Log x, differentiate is 1 over x. Minus 1 over x, differentiate 1 over x squared. And see whether or not this time you can evaluate the limits. Well, let's x approaches 1 from the right-hand side. This approaches 1. This approaches 1, this approaches 1, so the whole thing approaches 2. Good news is not something that is indeterminate. The answer is 1 over 2. So because the answer is 1 over 2, so everything that we did right here, everything works out. So this 1 over 2 is actually this limit. So you can see some complicated problems do have to, you do have to use the L'Hopital rule twice. Okay, now finally, last thing we want to talk about is indeterminate power. So this type of things, okay, is indeterminate. And by now you should know what I'm trying to say. There is no such thing, okay? There's no notation. These are not real thing. This is just simply means that we are looking at, for example, this one just simply means that we are looking at the limit of this type, fx, and then gx to the power, right? And then the f goes to 0, g goes to 0 when x goes to a. Then we say this limit is indeterminate of this form, of this type, of this type. So don't ever go back and tell your younger brother, younger sister that in university there is really a such thing. There's no such thing. That doesn't mean that, okay? There's no such thing either, all right? So it just means that we have a limit where that of this type where the f goes to infinity, your g goes to 0, then when x goes to a, then you say that, well, we are having indeterminate limits of this type, okay? Right, so enough of this. Let's see how we're going to deal with it. This is a little bit more involved, so a little bit of review. So if you remember from Calc 1, this is how your professor mentions about the concept of continuity, right? It says that if your f is continuous as a number alpha, your book use a, but you know, if you write a here, it's confusing. You'll be like f is continuous at a number Eve. So in order to avoid that, I'm just going to use alpha. So recall Math 151. When you have a function which is continuous at the number alpha, it means that these three things, f alpha have to exist, this limit have to exist, and not only that, the limits that you get right here has to be the same as f alpha. So that's the concept of continuity. Your professor maybe do not show you this way, but this is exactly what it said. Because the alpha, okay, f alpha, the alpha is exactly this. So they are saying that a function, if it is continuous, you have this. For example, e to the power of x is a continuous function. So if you evaluate these limits, you can just bring the limits into that function like this. So evaluating these limits is the same as this. You have this. It's a notation that you might not be very familiar with. That's the reason why we put it here, to show you this, saying that the things that you learn in Calc 1 is the same thing we can say it this way, and when you apply it, you can apply it this way. And actually what we want to do is a little bit more fancy. It's the same concept. but is involve composition of functions, which means that if your f is continuous, if your function f is continuous, you can still bring in the limits like this. So if you're asked to compute this limit, it's the same as computing this limit if the f is a continuous function. For so if you apply to the ex function, which is continuous functions, so what I'm saying is that evaluating this limit, right here in these situations, I'm using fx as ex. So this left-hand side here is exactly this. The right-hand side here is exactly this. That's what it means. Okay. So for a continuous function, especially e to the power of something, and you try to evaluate this limit, it's the same of evaluating the limit like this. Okay. This is critical. Make sure you know. Another thing that I want to remind you is that the exponential function and the log function are inverse of each other. We talked about that before. That's the reason why you also have this relationship, which means e log. Remember the slightly more general one is like you have a base b and then you have log base b and then you have that thing. That thing will equals to this, which means e, if you take b equals to e, then this is natural log, and then have this will be this. So let's say this is x, this will be x. If this is hard, this will be hard. If this is y squared, like say this is sine x, this will be sine x, so on and so forth. Okay. Now, so we are ready to look at this final few example. So limit of x to the power of x when x approaches 0 from the right hand side. How do you evaluate this? Well, this is what we call 0, 0 case. Okay, because this limits if x goes to 0, this goes to 0 obviously, and this also goes to 0. So the way we deal with it is to bring in the exponential function and rewrite this as this. Okay, why is that so? Because of this, right? E log x to the power of x is x to the power of x. So we are rewriting this using the exponential function. Why do we want to use the exponential functions? Because exponential function is continuous. And also the log function here allow you to use the log property to bring the x to the front. So you have that. And this is still this, nothing changed. We haven't evaluated the limit yet. And because exponential function is continuous, when you evaluate these limits, you can bring the limits up there. Just like what I'm saying right here. You might need to pause the video and think about it if you are not comfortable with this. But this is exactly what in Calc 1 your professor tell you, that e function x is continuous. It means that you can take limits like this. Okay. Now, so which means that we are turning these limits here into this, which means that we will know the answers if we know what this thing is, right? We will know this answer if we know what this limit is. So one way to approach this problem is to pause this for a little bit and reinvestigate this limit, which is something you already know how to deal with it, because when x goes to 0, this goes to 0, but this goes to infinity. So it's like 0 infinity type of problem, and you know how to deal with it by changing it into this, by changing it into infinity or infinity type of questions. And then this allows you to use L'Hopital, which give you derivative of this is this, derivative of this is this, which give you this, which give you 0, which means that we know what this limit is. We know this now. The limit is 0. So this thing here will be e to the power of 0, which is 1. That is how we solve it. Okay. It's significantly different from all the previous examples, so you might have to think about this for a little bit, but like that is how we solve it. Now, these techniques carry over to all type of problems which involve indeterminate power. You change it to exponential functions and use the property of exponential functions to find the limits. Now, recall that last time we kind of like computed separately. You can also compute it in one single setting, which is like this. Not really encourage you to do that. You might want to split it into two parts, but you can also do it like this. So x goes to infinity. You have this part here goes to, can you see it? when x goes to infinity, this part here goes to 0, obviously, and 3x goes to infinity. Sorry, let's go to 1. So 3x goes to infinity when x goes to infinity. So this is the type 1 to the power of infinity. Okay, indeterminate form of the type 1 to the power of infinity. And the way you deal with it, same thing. Change it into this. Okay, remember e to the power log of something, that box, that is that box. So I am using this right here, and I am using the log property to bring the 3x to the front, and I am using the continuity of the functions ex to bring the limits to the top. Okay, seeing how I bring the limits to the top, so this limits is right here, but now it's on the top, it's in the power section. Okay, so we will know what happened to the answers if we can compute this limit. So we can do it in one single setting without changing it to like some other stuff. So again, we're rewriting the power as this. Okay, bring the x down right here, so that now when x goes to infinity, I have log 1, which is 0, and then I also have 0. So you have indeterminate form 0 is 0, which allow you to use L'Hopital. So you take the derivative right here to get this. Okay, chain rule, you have to do that. Take the derivative, you get this. So that's just that, no big deal. Just applying L'Hopital and simplify the expressions. High school algebra, simplify it, pretty easy. This thing cancel out. 3 and 2 make 6. And then you have this limit. So as you can see, when x goes to infinity, this goes to 0. So the whole thing goes to 6. So you have that. So it's the same as before. Make sure that you know how to write all this thing in this and use the property of continuous functions. The exponential function is a continuous function to bring the limits from the bottoms to the top. And then the rest is the same. No big deal. One last example. We're using this a lot, okay? We also use this a lot, okay? Right, we also use this a lot. This one here, this kind of concept, make sure you know. And all right, one last example, which is this. Okay, I'm just OCD that you don't know what I'm saying. So make sure that you know that e to the power of something, log something, you will get that something. And then limits of x goes to a e of fx. I used gx before, let's stick to that. It's the same as bringing the limits to the power to the people or something. Okay, so bring it from the base to the power. We can do that because of the continuity of ex, the exponential functions. Okay, cool. Now, all right, last thing. This is a type of infinity over 0. Sorry, infinity to the power of 0. Because when x goes to infinity, x obviously go to infinity, 1 of x go to 0. Same thing, as long as it is indeterminate power of all this type, the solution method is the same, which is first thing you do, right, in terms of x, exponential of something. I skip a step, you can see that skipping steps now they're supposed to be here, but I already bring it down. And I'm bringing the limits from the base to the power, and then now I have to work this thing out, this limit. And this is infinity over infinity, L'Hopital rules apply. Differential log x gives you 1 of x, differential x gives you 1, which means that this thing is actually this, which is 0, and the whole thing will be 1. Got it? And that's that. Perhaps the most complicated part is this. Sections right here, indeterminate form of all this indeterminate power, because it utilizes fact number 1. Fact number 1. Fact number 1 and fact number 2. But they are all the same. You just need practice, practice, and practice. Okay, it's getting late. It's 8:14 right now. What day is it? Tuesday night. It's supposed to be freezing out there. So I am going to stop right here, and we'll try to make the video for the section 7.1. And make sure you know all this. It's not very complicated, and you will have a test on all this limits on Friday. All right, stay warm. See you later.